Hello everyone. In this video lecture, we are going to learn about synchronization hardware. In my earlier video, we have learnt a software-based solution called as Peterson's solution to the critical section problem. In general, any solution to the critical section problem requires a simple tool called lock. Race conditions can be prevented by locking the critical regions of code. Let us see a typical solution to the critical section problem using locks. If any process wishes to enter into critical section, it can do so by acquiring lock. And it should release the lock when it comes out. When it wishes to enter critical section, it needs to acquire the lock. It should gain ownership of the lock, and while it exits off the critical section, it needs to release the acquired lock. Okay. Today we are going to learn techniques to solve critical section problem by designing and using sophisticated locks. Hardware instructions we are going to learn today. The hardware instructions can make programming task much easier, and also it will improve the efficiency of the system when compared to software-based solutions. In a uniprocessor environment, critical section problem can be easily solved by disabling interrupts while processing a shared variable. And this approach is generally used by non-preemptive kernels. But however, this is not feasible in multiprocessor environment because disabling interrupts will be time consuming in such a model. You have to disable the interrupts in all the processors involved in the system, which takes lot of time. And also there is another problem. What if your clock is incremented using interrupt itself? Let us now learn two hardware instructions to solve critical section problem. The hardware instructions are atomic instructions in the sense they are non-interruptible. What do you mean by non-interruptible? Once you start execution of this instruction, it cannot be interrupted in between. The instructions that we are going to learn today are test and set instruction, which will test a memory word and set the value. The instruction name is test and set. And another instruction is swap instruction, which will swap contents of two memory words. So now let us start with the test and set instruction. It is a special instruction that does two operations atomically. That is, the instruction cannot be interrupted in between atomically. Please note, this means instruction cannot be interrupted in the middle, and it is not necessary to disable interrupts as well. Test and set, it is a privileged instruction, and if you have to execute this instruction, you require super user privilege. There is a memory location called as lock. Let me write here. There is a memory location called as lock, which is a shared variable, and it holds a Boolean value. Boolean value means it can hold either true or false. And initially this lock variable will have a value false. Okay. The value true indicates that if the value held in the lock variable, if it is true, that indicates that lock is already acquired by some process. And a false value here indicates that lock is free. And here is the code for test and set instruction. This looks like we are executing 3 instructions, but these 3 instructions are executed in one stretch without receiving any interrupts in between. The test and set instruction writes true value to lock variable, and it returns its old value of lock to the process which is wishing to enter into the critical section. in a single uninterruptible operation. Let us try to understand this test and set instruction with an example. Initially, the global Boolean variable lock will be set to false, as I said. Let's say process P1 wishes to enter into the critical section. If it wishes to enter into the critical section, this is a typical structure of a process. You can see that there is a while loop which calls test and set of lock. The current value of lock is passed as parameter for the function test and set. So it sends false here, and that false value will be whatever lock value, old lock value, it will be initialized to result. And the process who is wishing to enter the critical section will assign target value to be equal to true, and it will receive the old value of the result. And if the process receives false as the result, that means lock was free. Now it has acquired lock by writing true into this lock variable. That means it can enter into the critical section. This is the portion where process P1 is executing its critical section. Meanwhile, if some other process, let's say process 2, wants to set the target to true because it also wants to enter into critical section, then what it will do? It will again call the test and set instruction. Now, when it calls test and set instruction, the lock variable value will be set to result. What is the lock variable value? It is true now. And this true is returned back to process 2. That means process 2 will get stuck in the while loop doing nothing at all until lock value becomes again equal to false. And when does the lock value becomes false? When process P1 exits the critical section. You can see the code. When any process exits the critical section, it will release the lock by setting lock variable back to false. Okay, please note that this synchronization mechanism ensures mutual exclusion, but it does not guarantee bounded waiting. That means some process may starve forever. Next, let us proceed. This is the code as it is given in your textbook. The logic already I have explained in my previous slide. You just go through the code, you will understand. The next hardware instruction is swap. Swap is another hardware instruction for process synchronization. This instruction does a complete swap atomically. It is complete swap, which means it requires 3 operations. Normally we know what is the implementation of a swap function, which minimally requires 3 operations, 3 instructions. But all these 3 instructions execute as if it is a single instruction. And what is the job of swap instruction? It operates on the contents of 2 words. A global Boolean variable lock is declared and it is initialized to false. And also each process has a local Boolean variable key. You can see that each process will have a local variable called as key. And also there will be a global Boolean variable called as lock. Initially this lock will be false. Whichever process wishes to enter into the critical section will set key to true, and if key is true, it will try to execute the swap. And what happens in swap? The key value and lock value will be swapped back. And if the swap is successful, then this process has successfully acquired the lock. And if the swap is not successful, that indicates that the process has not acquired lock because some other process is executing in its critical section. And if it has acquired lock, then it can enter its critical section to modify the shared resource, and when it exits of the critical section, it will store the lock value back to false so that some other process can which are waiting to enter the critical section can now do so. Okay, so this is about the swap instruction. Again, please note, both TestAndSet and swap instructions satisfy the mutual exclusion property, but it fails to satisfy bounded waiting. So let me now present you another algorithm using TestAndSet instruction that satisfies all three requirements of critical section: mutual exclusion, progress, bounded waiting. All three requirements are satisfied with the new algorithm that we are going to study now. And this algorithm, it uses two data structures, waiting, which is an array of n numbers. This n, it is a representation of how many number of cooperating processes are there, and there is another boolean variable lock, and whole of this waiting array to represent n number of processes which are cooperating with each other are set to false initially, and also the boolean lock variable is set to false. Now if some process wishes to enter its critical section, then it will set its corresponding wait value to true. It will also set key value to true. I'll use some other ink. Whichever process wishes to enter critical section will make its corresponding value in the array to be equal to true, and also it will set a local variable in its own process called as key to true. Now it will enter into the while loop. What is the condition for while loop? If waiting is true and also key is true, then it will try to execute TestAndSet instruction. We have already learned to TestAndSet instruction. If lock is free, the process will receive false. If lock is occupied, the process will receive true, right? If it receives false from the TestAndSet instruction, for example, then it will make its waiting equal to false, which indicates that it is no longer in waiting state because it has successfully acquired the lock. When it has successfully acquired the lock, it can enter into the critical section to modify a shared resource. While it comes out of the critical section, it will try to execute a statement where it will increment the value of I by 1. Okay, and that value will be assigned to j. This process and the while loop following it is to determine which other processes are currently waiting to enter its critical section. If any of the process wishes to enter critical section, then it should have set its corresponding waiting value to true, which breaks this while loop. You can see if waiting of j is false and also if I value is equal to j, then you are incrementing the value of j by 1. And when are we coming out of this while loop? Whenever a process waiting is equal to true, then we are coming out of the while loop. This is one condition. Let me take this condition first. When any of the process waiting is equal to true, then we are coming out of this while loop. But what is its significance? If any of the process has set its waiting to true, that indicates that it is wishing to enter into the critical section. In that case, it no longer has to wait because lock has been released by the currently running process. Now the waiting process can acquire the lock. Right? The waiting process can acquire the lock by making waiting of the requesting process equal to false. Anyway, the requesting process has made already the key value to be equal to true. And if the new process, the new j value after doing this computation, that is j plus 1 mod n, if it is equal to I, what is its significance? It indicates that you are speaking about the same process which have already completed its critical section execution. That means you have to release the lock, and also this condition indicates that there are no other process waiting to enter their critical section. To make this algorithm clear, I have written one example here. I have considered a 5 number of cooperating process. So our waiting array will have 5 number of elements. Initially they are all set to false. And also there is a global boolean variable called as lock, which is also set to false. Now let's say process P3 wishes to enter into the critical section. What is the first line of our code? We have to make its corresponding wait value to true. Waiting of 3 should be made equal to true. Then we have to set the local variable key also to true. Now we will check the while loop to call the test and set. Waiting of 3 is true. Yes, it is true. Key value true. Yes, it is also true. That means you can call the test and set instruction. And how test and set instruction works? It will check the lock value and it will return the lock value back to the calling process after setting true here, after writing true in the locked region, right? So what test and set instruction do? I repeat, it will take the current lock value to some local variables, to some temporary variable, right? Then it will set the lock value to true and it will return the old value back to the process. So what is the old value returned now? False. So process P3 receives false because initially lock is false. And what is the significance? When key value received is false, that indicates that process P3 has successfully acquired lock. It has successfully acquired lock. Now lock value is true, right? And after acquiring the lock, what it will do? It will make waiting value of 3 to false because it is no longer waiting for entering into the critical section. It has acquired the lock. It is modifying a shared resource by executing its critical section. Meanwhile, if some other process, let's say process P1 wants to enter into the critical section, it can do so by turning its waiting element in the array to true. P1 will change this to true. And also its local variable key will be set to true. Then it will try to execute the test and set instruction. When it executes test and set instruction, what happens? What is the current value of lock now? True. So process 1 will receive true. When it is true, can it proceed? No, it cannot proceed. It cannot proceed. So it will be repeatedly executing the same instruction. And while the process P3 finishes its critical section, what it will do is it will increment the value of I by 1 and assign it to j. What is the current value of I? It is 3. It will increment, which will become 4. 4 mod 5 is 4 itself. Now j value is 4. Now check the next while loop. J is not equal to I. Is that right? J value is 4, I value is 3. So this condition is satisfied. Waiting of j is equal to false. Waiting of 4. Waiting of 4 is equal to false. Yes, it is also true. When that is true, what we are trying to do? We are incrementing the j value. Now j will become 5. Again, check the condition. J is equal to I. Let me write I value here. I, we are not changing. It is still 3. We are again checking whether I value is equal to J. No. So this condition satisfied. Next condition is weighting of J is equal to false. Yes, weighting of J is also equal to false. Then again what we have to do? Again increment the J value by 1. When you increment J value by 1, what happens? It is 6 mod n, 6 mod 5. How much is 6 mod 5? J will become 1 now. When J becomes 1, again check the condition whether J is equal to I. No. I is 3, J is 1. So this condition is satisfied. Weighting of J is equal to false. Weighting of 1 is equal to false. Now the condition fails because weighting of 1 is true, because process 1 is waiting to enter its critical section. So it has already set weighting of 1 to true. When it gets that, this while loop breaks. When loop breaks, now again we will check the condition if I value is equal to J. No, because I is 3, J is 1. Then we are going to execute the else part. What we are going to do in the else part? We are making weighting of J to false. Now we are setting back this weighting of J to false again. What is the significance of setting weighting of J to false? That indicates that you no longer have to wait, because now weighting of 1 is true, key is also true. When both these conditions satisfy, that means it can come out of the while loop. What was the while loop? Weighting of 1 is equal to true and key is equal to true. If both the conditions are satisfied, then we will exit the while loop. This indicates that we have successfully acquired the lock. Now process 1 can enter its critical section. Now I will leave you when does I value will become equal to J, why this lock will be set to false in that condition. With this, I conclude this session. Thank you. Let us now learn the concept of semaphore. Originally, semaphores were flags for signaling between ships by holding two flags in certain positions according to an alphabetic code, as you can see in this slide. But in operating systems, semaphores are integer variables that are used to solve the critical section problem. Here also they are used to signal the availability of the resources. Semaphores can solve critical section problem, as I said, by using two atomic operations called as wait and signal. Apart from initialization, semaphore can be accessed only through these two atomic operations. Initialization of a semaphore is done before any process tries to operate on it. And wait operation is for acquiring the resource, and signal operation is for releasing the resource. The wait operation was originally called as P, which stands for a Dutch word proberen, which means test, and signal operation was derived from another Dutch word called as verhogen, which means to increment. I summarize. Wait operation is used to check or test whether semaphore is available so that a process can enter into the critical section. And V operation or a signal, it is used to release the resource after it has completed the critical section execution. In this slide we have the definition of wait and signal. Please note, initially semaphore will have some non-negative value. it will have some non-negative integer value, and this non-negative integer value will be altered by wait and signal functions. The wait, if it is successful, it will decrement the semaphore value by 1, and signal will increment the semaphore value by 1. Please understand how the wait works. Whenever semaphore value is less than 0, if it is a negative value, then process cannot acquire the lock. That means it cannot enter into the critical section, in which case it will continuously loop in this while, checking when the S will become a positive value. And whenever S becomes a positive value, it will acquire the lock, enter into the critical section, and also it will decrement the value of S by 1, indicating that it has used the shared resource. Similarly, whenever a process completes its critical section execution, it has to release the lock. When it releases the lock, it will increment the value of S by 1. So this is how wait and signal operations are defined. Let us move forward. Basically, there are two types of semaphores available: counting semaphores and binary semaphores. Counting semaphores counting semaphores can have an integer value which can range over an unrestricted domain, minus infinity to plus infinity, which depends on the how many number of resources are available of a particular kind. And binary semaphores can range only between 0 and 1. Binary, as the name suggests, it will take up a value either 0 or 1. So binary semaphores are much easier to code. They are also called as mutex locks because they can be used to implement mutual exclusion. Mutex is mutual exclusion. Okay, a typical application of binary semaphore is handling critical section problem for multiple process. Let us see an example to understand how binary semaphore can provide mutual exclusion for a critical section problem. But before that, let's see a typical process structure which uses this mutex to solve mutual exclusion. Okay, you can see here a mutex is a semaphore. Mutex is a semaphore which can take upon a value of 0 or 1, since this is a binary semaphore. And whenever a process requests to enter into the critical section, it has to call the wait operation. The wait operation, just now we have learnt, will decrement the value of S by 1 only when the current semaphore value is a positive number, and it will enter into the critical section. And when the critical section execution is completed, it has to release the resource. While doing so, it will increment the value of mutex to 1 back. That means if mutex value is 0 or less than 1, that means the resource has been occupied already by some process. The requesting process has to wait. If mutex value is 1, the requesting process will get hold of the semaphore and it can enter into the critical section. To clearly understand this, let us take a simple example of a system containing only two processes, let us say P1 and P2. Okay, let's say both the processes are currently executing in their non-critical section, and also let us assume that mutex value is 1. When process P1 wishes to enter into the critical section, it will perform the wait operation on mutex. Since mutex value is 1, it can enter into the critical section. While doing so, it will decrement the semaphore value by 0. Semaphore value by 1, which makes it 0. Meanwhile, if P2 also wishes to enter into the critical section, it has to again execute the wait operation. But what is the current value of mutex? It is 0. That means process P2 will get stuck in the while loop. When process P1 finishes its execution, critical section code, then it will release the resource. When it releases the resource, it will also increment the mutex value by 1. Right? How does it do it? By calling the signal operation. So the process P2 was waiting for this to happen. It was waiting for mutex to become a non-zero value. Now it has become 1. Then P2 can enter into the critical section and the process continues. Next, let us discuss about counting semaphores. Counting semaphore can be used to control access to a given resource consisting of finite number of instances. Let me clear this. Let us try to understand counting semaphore with an analogy. Suppose, let us say there is a hotel lodge with 3 rooms. 3 rooms. Okay. Which can be occupied one person at a time. One room, only one person can occupy. So if a person requests for a room, he has to go to the front desk in the lodge asking to use the room. If no rooms are free, then people have to wait. People have to wait at the desk until someone checks out of the room. When a person has to check out, he must return key to the desk and indicate that one room has become free. In the simplest implementation, the receptionist at the front desk knows only the number of free rooms available. When a person requests a room, the receptionist decreases this number, and when a person goes out of the room, the receptionist increases this number. In this scenario, the front desk count holder, it represents a counting semaphore. I repeat, in this analogy, that count, total number of rooms available, will be counting semaphore value. The rooms are the resources, and the person requesting for the room can be treated as process or threads. Value of the semaphore in this scenario will be initially 3, with all rooms being empty. When a person requests a room, he can be allotted the room after changing semaphore value to 2. Now let us assume another person is coming in requesting for the room. Again the value drops to 1. And let us assume that there is one more person coming asking for the room. Again the semaphore value dropped to 0. If now someone requests for a room, are there any more rooms available? No, because semaphore value has already reached 0. 3 persons have already occupied 3 rooms. Now the 4th, 5th, 6th, any number of persons coming now, they has to wait until room becomes free. Right? So this is the analogy of semaphore. Let us summarize. Technically, counting semaphore can be used to control access to a given resource consisting of finite number of instances. The semaphore is initialized to the number of resources available. To use a resource, process needs to perform a wait operation. That means the semaphore has to be decremented by 1. When process releases the resource, it performs a signal operation by incrementing the semaphore value by 1. And when the count for the semaphore goes to 0, that indicates that all the resources are being used. Then the process has to go to the waiting state. So this is about counting semaphores. We have 2 types of semaphores. counting semaphore and binary semaphore. In case of counting semaphore, integer value can range over an unrestricted domain. In case of binary semaphore, it can range only between 0 and 1. Okay, I hope this slide is clear. I'll proceed. Next is how semaphores are implemented. The main drawback of the semaphore definition that we have studied so far is busy waiting. What is busy waiting? While a process is executing in its critical section and any other process that tries to enter into its critical section must loop continuously in the entry code. Have you observed? I have cleared. See, this is our wait code, and let us say we have two processes. I go back to my earlier example of binary semaphore P1, P2. Initially semaphore value will be 1. P1 executes wait on yes. It can successfully enter into the critical section. But P2, when it also wants to execute the critical section, first it has to execute the wait operation. But what is the current value of the semaphore now? It is 0. So when it is 0, what process P2 is doing? It is continuously stuck in this while loop itself. It will check whether S has become positive. No. Again it will check. No. Again it will check. It is busily waiting for the semaphore value to become a positive number. Right, and this operation is not a useful operation. CPU is not productively used here. This type of semaphores are also called as spin locks because process spins while waiting for the lock. To overcome the busy waiting problem, we have modified the definition of wait and signal operations. Observe the wait function. Now before that, with each semaphore there is an associated waiting queue. Please note, each entry in a waiting queue has two data items, value and pointer to next record in the list. Now observe that wait function, whenever S value is negative, instead of engaging in a while loop, here was a while loop in our earlier definition. Now instead of engaging in busy waiting, the process will block itself. The block operation places a process into waiting queue and the state of the process is switched to the waiting state. A process that is blocked waiting for some semaphore yes should be restarted when some other process which was executing in its critical section executes signal operation. We know that the signal operation will increment the value of semaphore by 1, and when semaphore value becomes a positive number, this blocked process can be restarted. And to restart the operation in the signal, we have wake up operation. Okay, in summary, the block operation suspends the process that invokes it and the wake up operation resumes the execution of a blocked process. Continuing with the semaphore implementation, there are few things that needs to be taken care while using the semaphores. We must guarantee that no two processes can execute wait and signal on the same semaphore at the same time. Such a guarantee is assured in a single processor environment by disabling interrupts. However, disabling interrupts in multiprocessor environment is a difficult task and it is also not much appreciated when it comes to the performance. We have not completely eliminated busy waiting with the new definition of wait and signal operations. Yes, we have not completely eliminated it. Rather, we have moved busy waiting from entry section to the critical section. Typically, critical section will have a shorter code and also busy waiting in critical section will rarely occur. So this implementation works fine most of the times. But if an application spends a lot of time in critical section, In that case, this implementation is not a good solution. The last part of semaphores is deadlock and starvation. We need to understand what is a situation called as deadlock and how the semaphore leads to deadlocks. To start with, deadlock is a situation where two or more processes are waiting indefinitely for an event to happen, and that event can be caused only by one of these waiting process itself. Some event should happen, but who will cause that event? Waiting process. And all the process will be waiting for an indefinite time. To understand this, let us consider a system of two processes P0 and P1. P0 and P1. You can see that a series of statements executed by process P0 and P1. Initially P0, before that we have two semaphores S and Q, both are initialized to 1. We have semaphore S initialized to 1, Q initialized to 1. Initially P0 executes wait for S. When it executes wait on S, what happens? Yes, is it available? Yes, it is available. So P0 gets hold of S. Similarly, at the same time, P1 is executing a wait on Q. Is Q available? Yes, Q is available. So P1 gets hold of Q. When P0 gets hold of S, it decrements 1 to 0. When P1 gets hold of Q, it decrements a Q value by 1, which becomes 0. Now process P0 is wishing for a semaphore Q. Is it available? No. Because Q value is 0, it has already been acquired by process P1. At the same time, P1 is wishing for acquisition of semaphore yes. Is it available? No. Already this yes is acquired by process P0. And when does process P0 can expect Q? I repeat, when does process P0 can get access for Q? Only when P1 releases it. How P1 releases it? By calling the signal operation on Q. But when does it do so? Only when it gets holds of yes. Similarly, when does process P1 get holds of yes? P1 can access yes only when P0 releases it. When P0 releases it, or how P0 releases it? By calling the signal operation on yes. But when does it do so? Only when it gets holds of Q. So P0 is indefinitely waiting for the resource Q, which is held by P1, and P1 is waiting for yes, which is held by P0. So this is the concept of deadlock. I hope this is clear to all. We have a dedicated unit for understanding deadlocks. My point here is semaphores can lead to deadlock, and another problem with deadlocks is indefinite blocking, which is also called as starvation. This is a situation where the process will wait indefinitely within the semaphore. The process will wait indefinitely within the semaphore. We call this as starvation. A process may never be removed from the semaphore queue in which it is suspended. You have pushed some process to the queue and it has never removed out of that queue. That we call it as starvation. And that's all about semaphores. In the next video, we are going to learn about classic problems of synchronization. Thank you.